Okay, so the Hall effect. If you have this wire, so here's our wire, and it's got this current going to the right, which means an electron, which is this little dot right here in the middle, would be moving to the left. Is going to, and we have a magnetic field going on here. You're going to get a Hall effect. The Hall effect being the force on the charges that are moving through the wire because it's a current. So the electrons are moving to the left. The magnetic field is coming out of the paper. We use our right-hand rule. We're going to stick our thumb in the direction of that velocity off to the left there. Whoa. Stick our thumb in the direction of this velocity. Our hand out of the page. Our palm would point upward, which would be the direction that a positive force would be forced. A positive charge would be forced. But it's an electron, so it's negative. So a negative electron will feel a force downward. And this creates kind of like a cross current. The electrons are already moving to the left, but they also start to move downward. And on this wire, what that's going to mean is it's going to polarize this wire. The bottom side is going to be negatively charged. The top will be positively charged. And that Hall effect is actually quite useful. You can use that Hall effect to detect magnetic fields. And that's very similar to how they detect magnetic fields using what they call a Hall probe. A Hall probe is a device that has some kind of electrical properties, some kinds of moving electrons. And as those electrons move through a magnetic field, they get forced to one side of the device or the other by the Hall effect, and then the device measures that movement and can therefore measure the magnetic field that is causing that movement. Of course, if it's positive charges that are moving, then your thumb would go to the right, which would be the direction of the current, and you get then you get a force downward, and the positive charges would go down instead of the negative charges. But the positive charges aren't the things moving, so that's not what's happening. So in normal wires, you get this negative side on the bottom and the positive side on the top for a current that's going right. Of course, if the current is going left, you get the exact opposite polarization. Negative charges on top, positive charges on the bottom of the wire from the Hall effect. From this idea, we get this equation, excuse me, sorry. Coming from Coulomb's law, Q times E, which is the movement of a charge in an electric field, that ends up equaling Q times V. And this is using in this particular case, we're using, they're using the example of using the Hall effect to measure the movement of blood in your body, because the blood in your body has charges on it, and so you can measure the movement of blood in your body by putting it in a magnetic field and measuring that voltage change. And the interesting thing about this equation is that you can divide out the charge. The charge doesn't end up mattering. The electric field equals just the velocity of whatever's moving times the magnetic field that you've applied. So that becomes quite interesting. And if you don't want to measure the electric field, you just want to measure the voltage, which is much easier to measure than electric field. Measuring voltage is quite easy to do. Then you can just measure the voltage divided by the distance across the flow of charge, or the thickness of the flow of charge, as it may be. And you get this equation here, where you get voltage per length, or voltage per width of your conductor, equals velocity of the charges, or velocity of the particles, times the magnetic field that you apply. And then, of course, you can write this equation, which is actually an equation that can calculate the voltage, but you could also rearrange it to calculate magnetic field. You do all kinds of things. But this is quite an interesting equation, because if you have anything that's flowing through a conduit, any kind of charge that's flowing through a conduit, you know the width of the conduit, and you apply the magnetic field, and you know the velocity, then you can calculate that voltage that should be there, or you can measure the voltage and calculate the other things, either way. So it's quite useful. And this is what they use to measure blood flow. So they put this Hall effect probe around blood vessels. They can put it around your arteries or your veins or whatever, and they can measure how your blood is flowing in different parts of your body. This can be external to the body, so it's especially on your fingers where there's not that much going on. But here we have an example where we're going to apply a 1.1 Tesla magnetic field across an artery, and then put this probe in place to measure that EMF. And they know that the diameter is 4 millimeters and the velocity is 20 centimeters per second. Usually what you'll do is you'll measure the EMF, you'll measure the voltage and calculate the blood velocity. That's what you really want to do. But that's okay. Either way, they're giving us the blood velocity, so we're going to calculate what the voltage should be. And it turns out you plug in all those numbers and you get 80 microvolts of EMF across that artery because of the Hall effect, because of the magnetic field that you've applied. That's easily measurable, so not a big deal. You'll find that more and more as we go through this class that there are so many applications of physics to medicine and other things, biology. And it's actually an entire field of physics and engineering. Almost every, in fact, I would go as far as to say 99% of medical instruments are invented and developed by physicists and engineers who have almost no biology background or medical background. That's not what their background is. Their background is physics. And so it's a very important field, and of course, they make that field has a lot of money in it. So it's a great field to go into if you have an interest in medicine. This idea of designing instruments. It's the biomedical field, in case you're wondering what they call it. They call it biomedical engineering or biomedical physics. So that is the Hall effect. Now we're going to apply that effect in a few different situations as we start to talk about forces on objects that are carrying currents. In this first situation, we're going to start with a wire that is carrying a current, and we're going to put it in a magnetic field, and we're going to figure out what kind of force is going to be applied to the wire. Okay? So here's our situation, right? We have a magnetic field that is going from left to right. We have a wire that is in this magnetic field that's coming out of the page. We use our right hand rule, put our thumb in the direction of the moving charge, which is in the direction of the current. So put your thumb in the direction of the current, right? We're going to put our hand in the direction of the magnetic field, which is across this way. So our thumb should be coming, well, for me it's this way, for you guys it's this way. Sorry, I'm looking at the wrong screen. So it's coming out of the thing here, hand across this way, right? And then our palm is pointing up, so the force on the wire will be up. So this wire will actually move upward. So you can actually use a magnet to move a wire, to move things. This becomes quite important here. The mathematics for this ends up being the length of the wire, because it depends on how much wire is actually in the magnetic field. So you have to measure the length of the wire that's going through the magnetic field. If the whole wire is in there, then you just put the whole length. But if not, then you only put the part that's in there. You take that length of the wire times the magnetic field, and then you multiply it by times n, which is the number of wires, because you might have multiple loops of wire, and you might have multiple wires in there, times the elementary charge Q, 1.6 times whatever, and then the cross-sectional area of the wire times the velocity, the drift velocity of the current. That tells you the current. N times Q times A times VD tells you the current that's going through there. So if you know the current, you can just replace this whole thing with I. You can replace it with the current and you'll be done. It would be just current times L times V times sine of theta. What does the sine of theta got to do with it? Well, the right-hand rule only gives you the direction of the force. But if the magnetic field is off, if is tilted a little bit, you won't get as much force. You'll get less force. So if the field and the wire have to be perpendicular to each other perfectly. If they're not perpendicular to each other, if the current is not perpendicular to the magnetic field, then if it's going through it at an angle, for example, and the magnetic field is coming this way and the current is going this way, so that they're not 90 degrees to each other, they won't get all of the effect. So you have to put in the sine of theta, which is the angle between the current and the magnetic field. And then you can get the magnitude of that force. So we have this figure down here where we have the wire going straight through. No, it's this one right here. We have the wire going straight through, so it is perpendicular to the magnetic field. And they want us to calculate the amount of force. And they tell us the magnetic field, they tell us the length of the wire, they tell us the current, we just plug them in. Current times length times magnetic field times the sine of 90, which is just 1. You have 1.5 newtons of force. It's a pretty big magnetic field, so you get a lot of force. Here they're showing the idea of what is called magnetohydrodynamics, which is one of the most complicated things in the universe to really deal with. But especially if you start adding electrodynamics in there too. But magnetohydrodynamics is the idea of using these magnetic forces that can exist to pump a fluid, to create fluid flow. So it's called a magnetohydrodynamic pump. And the idea is that you can move a fluid without any moving parts, without any mechanical parts. This has great advantages in many situations. If you ever watched the movie Red October or read the book Red October, it was about a submarine that used these kinds of pumps to move through the water. Very interesting stuff. But in this case, you have a current that's going through the fluid. So it's going across the fluid this way by this circuit. This circuit is causing this current to go through the fluid. And if you put your hands in the correct ways, you have your current that's going down, so there's your thumb down, the magnetic field which is off to the left, and the force will be out of the page, and that will push that fluid through. The only real bad part to this is that the fluid has to be something that can carry electricity. And salt water is great. But the pipe that this is in has to be made of something that is not going to be corroded by salt water with electricity passing through it. And there are very few things, especially very few metals, that will allow you to pump electricity through them and salt water and not be corroded. They almost always start to corrode badly. Electrolysis is a huge problem. So this has to be done very carefully, and it's very difficult to do it properly, to do it well. But it can be done. Here they show it in a submarine. And they talk about the Hunt for Red. How many of you have seen The Hunt for Red October? Great movie. Probably the best submarine movie ever made. Okay, so now let's move on to something a little more complicated. Same idea, forces on wires with currents going through them. But now the magnetic field, now the wire is no longer just a single wire going through the magnetic field, but a loop of a wire. So the wire is looped around. The current is going up this side and around the loop and then back down through the magnetic field. So in other words, the current is going both ways through this, and not only both ways, but it's going 4 different directions through. What are the 4 different directions? It's going up, it's going down. What other directions is it going? From this direction to this direction, left to right, kind of, whatever, and then this direction to this direction on the bottom of the loop. So it's got 4 different directions. Let's figure out what are the forces on these 4 different directions inside of this magnetic field. Okay, this is another quiz for you. Get out a piece of paper, and it's another right-hand rule quiz. You have 4 directions. You have magnetic field going from left to right. You have current going up on one side, current going down on this other side. You have current going this way. It's not exactly, in fact, let's do this so that, everybody look up here really quick. We're not going to pretend that this thing is at an angle in here. We're going to pretend that this thing is going, this loop is turned this way, so that the loop is perfectly parallel to or perfectly The loop is perpendicular to the magnetic field. So the magnetic field is going straight through the loop. And you have a current going into the page, a current coming out of the page, a current going up, and a current going down. I want you to figure out the forces on each one of those currents due to that magnetic field. You have a current going in, a current coming out, a current going up, a current going down. The force on each one of those if the magnetic field is going from left to right. All right, you guys done? Let's turn them in if you're done. Huh? What do you mean? I just want the direction of the force on the wire. And for that one, it does current. You put your thumb in the direction of the current. So, yeah, it's the force is coming out of your thumb.
So on both the probably going across and probably going
Well, yeah, we have a wire that's going up, that has a current going up, a wire that has a current going down, we have a wire that has a current going into the page, and a wire that has a current coming out of the page. Okay? The current, the one on the top has the current going in, the one on the bottom has the current coming out. So we're not gonna pretend like it's an angle here. We're gonna pretend that like this thing is turned perfectly to the page. So it's going into the page on the top and coming out of the page on the bottom. One force for each of those. One direction for each force. So I'm thinking for a STEM club meeting next Wednesday at 3 o'clock. So I will send out an email to everybody in the STEM club if anyone wants to join the STEM club. It looks good on your college transcripts and your college applications and resumes. And you'll also have the opportunity to go with this link if we can get that organized. All right, we got this done? It is the 15th of February. It's my wife's birthday. Okay, so now explain to each other which directions those forces are. Once you guys come to an agreement, you guys back here are going to decide which direction the forces are on the upward current and the inward current, upward and into the board. You're going to do those two, and you're going to report to the group what you think it is, and you guys are going to do the bottom one, or the downward one, and the bottom one that's coming out. So it's going to be the downward current and the coming out current. You guys decide which way those forces are going, and then justify them in the class. From the from the direction of the current, right, and the direction of the magnetic field, follow the direction of the force.
That's the current is going out. Magnetic field is yeah, force would be straight around.
You guys ready? Okay. Who wants to start? Okay, you guys start up here. So tell me what we got. You guys are doing the downward and the outward current. So what force do we feel from the downward one?
It's going into the inside
It's going what?
of the inside of the loop.
Okay, so it's going across the page. So let's do the right hand rule. The current down, magnetic field is to the right, right? So we're feeling a force that's outward, that's essentially perpendicular to the loop, right? And they show it there, so that's kind of nice, right? What about the one that's coming out of the page? We have our thumb coming out, magnetic field to the right. Which way is the force? Magnetic field or current is coming out of the page. Magnetic field is to the right. Which way is our palm pointing? It's up, right? That force is up. Okay, so we have one force on the loop that is pushing the side of the loop one way, right? It's good for that one that's going down. We have down this way, so it's pushing it essentially out of the page. We have a force out of the page, and we have a force upward on the loop. Okay, what's yours? So the upward, so for the upward current, which way is your force? Upward thumb is up, magnetic field is to the right, so it's
Going
into the page. So we have one force on one side of the loop outside the page, one into the page, and those two forces are separated on either side of the loop. What's that going to do to the loop? If you take a force, it's going to make it spin, right? If you take a force and put it on one side of an object going one way and the other side of the object going the other way, it turns the loop, right? It creates a torque, like we learned last semester. So it's going to rotate this loop as long as that loop is free to rotate. And that's what we do. We put that in the center of that loop, right down here. We put an axis with a little ball bearing thing or something, and we let it spin that way, right? What about the current that's going across the top? Current that's going across the top is going into the page, thumb in, magnetic field to the right. What way is the force? So we have a force down on the loop from this top one and up on the loop from this. What are those two forces going to do?
spin.
No, it's going down and up directly towards each other,
Cancel each other.
right at the center of the loop. They're just going to cancel out. Those forces don't do anything. So the top of the loop and the bottom of the loop don't do anything, but the sides, they cause the loop to spin. What do we call this device? Where you put an electricity and it spins. I'm sorry? A merry-go-round? Merry-go-rounds can be functioned like this. But what is the device called? We use this device in all kinds of things. What? I can't hear what you're saying. Detector. What would it detect? It's even similar than this. I mean, it's even simpler than what you're trying to make it into. If like this morning I got up and I put blueberries and yogurt and grape juice into my blender, and then I switched a switch and it turned something on inside the blender. What is that thing that makes the blender blend? It's a motor. That's what this is. This is the same thing that causes your phone to vibrate. They have a little motor inside of your phone that has a little mass on one side so that when it spins off axis, it gets all wiggly and it causes your phone to vibrate. It's the same thing that when you have a bunch of junk in your sink and you want to grind it up, you turn on your motor in your disposal and it grinds it all up. It's electricity that goes through a loop that is inside of a magnetic field and causes something to spin. It's a motor. So, welcome to your first application of electromagnetics. And really probably one of the single most important applications that there is. We use this particular device in so many situations. It's not only a useful thing to drive a current through it to make it spin, but if you spin it without a current going through the wire, it actually create a current through the wire, and then you can make electricity. This is actually also what we call a generator. So, how do we do the math of all this stuff? Well, the torque is equal to distance times force. The distance is the width of the loop divided by 2, because you get 2 of these forces, times force, and you add them together, so it ends up just being the width of the loop, total width of the loop times the force, times the sine of the angle between the loop and the magnetic field. Because if the loop is not directly in line with the magnetic field, the forces are different than when it is. Okay? So, if it's off kilter a little bit, then you have to use the sine of theta. If it's directly in line, then the sine of theta is just equal to 1, and it doesn't matter. The problem is that when you're directly in line with the magnetic field, those forces are very strong. But if you're lined up, so in this particular case, your loop, this is one side of the loop, this is looking from the top, the other side of the loop, and this is the axis of the loop. When you're in this situation, you get these forces that actually point outward like this, and the loop will just get stuck here. If you're at an angle, the forces try to push it into this position. If you're directly lined up with the field, if your loop is kind of lined up parallel with the field, then you have a maximum amount of force. So when you're here, you really want to spin so that you're here. When you're here and here, you kind of want to spin so that you get to here. But once you get to here, it will just lock up because your forces are going to cancel each other out. So you have to fix your motor so that it never gets locked up. So what you do is instead of allowing it to lock up in this position, every time it gets close to this position, you switch which direction the current is going. And if you switch which direction the current's going, it will keep spinning. And if you keep switching it, it'll keep spinning, keep spinning, keep spinning. Anyway, in any case, this is the equation that will tell you what the torque is on this loop. And if you have many loops, if you loop it many times, loop the wire through many times, then you just multiply that equation by n, and you get the torque that's on that. And here we can calculate that torque easily. They just tell you all the numbers, you throw them in, you get an answer. That's great. But how are we going to make this switch, how are we going to make the current switch directions? It's actually a pretty simple idea, but it's ingenious. Well, many simple ideas are ingenious. So here's our loop of wire right here. The current is going through in a clockwise fashion at the moment because it's connected to a battery down here, and you can see this connection down here. But the interesting thing is, as this loop turns and it gets into this position where it wants to lock into place, these connectors disengage from these two. What we call these two things here commutators, and we call these brushes. So the brushes disconnect from the commutators because there's a gap there. And so once they disconnect, the forces disappear because the current is gone. There's no more current. Once those forces disappear, that loop will just keep turning unless you stop it. So it keeps turning all the way through until it connects again. But the next time it connects going the other direction. The current is now going opposite the direction it was. But since the loop is turned, the motor still thinks it's going in the same direction because the loop is turned back around to where it was before. And then the current starts again because the brushes make contact with commutators again. And then the forces start again, and it keeps turning. It keeps turning and keeps turning. So it's like on being on a swing, or have you ever been on one of those swings that's a tire that you can spin somebody on? It's, you know, it's like when you spin them around, and then as soon as your hands go so far, you can't push them again. So you move your hands again and push them again. And that's kind of what's going on here, is that once you get to a certain point where this thing is going to lock up, you release it, and then you wait for it to go around, and then you lock up again and push it around again with new current. So now it's time to watch a video. Let's see, we don't want an AC, we want a DC motor. Here's a good one.
You can find DC motors in many portable home appliances, automobiles, and types of industrial equipment. In this video, we will logically understand the operation.
Okay, so right here I'm going to show you the similarities between this motor and the motors we've got. What we've got up here is the magnet. This is an iron core, and it's connected to a magnet. So there's magnetic field, but it's not just one magnet, there's many magnets. And then instead of having just one coil and one loop, they actually have many loops that are in different orientations. So this motor is much more complicated. If you just have one loop, you're only pushing it around once. But if you have multiple loops at different angles, then you can push it around more often. So it makes a smoother motor and a stronger motor and a faster motor. Because it's like having many people pushing the tire around and around instead of just one person who just pushes it once every spin, right? So that's the idea. But when you do that, each loop has to have its own set of commutators. So up here you see all these different commutators. Each one of these connections with a break in it is a commutator, and it has another one on the other side that makes the commutator pair. And then the brushes are on the outside over here. And as this thing turns, then one of the loops is going to be lined up in the magnetic field just right to get pushed around the loop. The magnetic field is actually an electromagnetic field. Here is an electromagnet that is created by a coil of wire with a current going through it. Here's the other side of the electromagnet. And the iron core around this creates that complete magnet. So this is a DC motor, much more complicated than what we just saw.
And construction of a commercial DC motor. Let's first start with the simplest DC motor possible.
So back to where we were.
It looks like this. The stator provides a constant magnetic field, and the armature, which is the rotating part, is a simple coil. The armature is connected to a DC power source through a pair of commutator rings. When the current flows through the coil, an electromagnetic force is induced on it according to the Lorentz law, so the coil will start to rotate. You will notice that as the coil rotates, the commutator rings connect with the power source of opposite polarity.
So right at this point, the rings should lock into place, except that the commutator rings are now going to switch places with sides of the battery. So the ring will keep going, and it will receive a little push around and new forces.
On the left side of the coil, the electricity will always flow away, and on the right side, electricity will always flow toward. This ensures
Then the forces
that the action is also in the same
are
direction.
always pushing this thing around and
The
around.
coil will continue rotating. But if you observe the torque action on the coil closely, you will notice that when the coil is nearly perpendicular to the magnetic flux, the torque action nears zero.
Okay, so magnetic flux is not something we've discussed yet, but flux is essentially the flow of field through an area. So in this case, we have the area being the coil, the inside of this coil, and the flow of the field lines through that coil is called the flux. The more flux that you get through a coil, the more torque that you're going to get, so you have more magnetic field.
As a result, there will be irregular motion of the rotor if you run such a DC motor.
So this one will kind of do this lopsided movement where it only gets pushed around one time per cycle.
Here is the trick to overcoming this problem. Add one more loop to the rotor with a separate commutator pair for it. In this arrangement, when the first loop is in the vertical position, The second loop will be connected to the power source, so a motive force is always present in the system. Moreover, the more such loops, the smoother will be the motor rotation. In a practical motor, the armature loops are fitted inside slots of highly permeable steel layers. This will enhance magnetic flux interaction. Spring-loaded commutator brushes help maintain contact with the power source. A permanent magnet stator pole is used only for very small DC motors. Most often, an electromagnet is used. The field coil of an electromagnet is powered from the same DC source.
Okay, so that's good enough for now. And you get the idea of how these things work. I actually have one here to show you live. Let me see if I can bring up my camera here. Wrong camera. So actually, yeah, that works. So I actually have this motor that I took out of I believe I took this out of a vacuum cleaner or something. But you can see the commutators down here. Each of those commutators, the loops of wire going through. And they also have an iron core in between each loop. That actually strengthens the motor power as well. So this is an interesting motor. This one is even more interesting. This is the fan from a computer, from a laptop. And the fan has actually got the magnet on it. The magnet is actually in the fan here. And this has the loops. So in this case, the loops are actually not moving and the magnet does move. How do they do that? Well, they do that by controlling the current through these loops. So they change the current through the loops using the computer, because the computer has brains to do that. And it forces this magnet to rotate around. The advantage of this type of motor is that it actually has no ball bearings. It has a spindle bearing, and the magnet actually floats on top of everything. So it has very low resistance, very low power usage, and very quiet. So different kinds of motors. For those of you that do have to leave, this will be recorded and I can send you the video link so that you can watch the rest of it.
So like that fan motor, it doesn't have brushes.
No, it doesn't, because the change in current, because the coils never move, so you don't have to have brushes at all. It's the magnet that moves. And this is called a what do they call this? They call this a, can't remember what they call this, but they have a name for it. The type of motor that this is, because you're changing the current using a controller rather than changing the current because of the movement of the coil. So it's a very different kind of motor, but a very useful one. Requires that you do have control of the current, though. You have to have something that can tell the current where to go. And so usually it requires some kind of computer to do it. Since a laptop is already a computer, that's easy. You know? So very useful. In the use of our ammeter voltmeter, like this Darsenball meter we showed you earlier, they're using the same concept. They have a coil that's between a magnet, and as a current goes through it that you're measuring, that current causes the coil to turn, and the coil is connected to a spring and a dial, and that gives you tells you how much current is going through or how much voltage is going through, depending on how you're using it. So it also can be used to measure things. So we've already done this idea. This idea was Ørsted's experiment. New right-hand rule, new idea here. If you just have a wire and you want to know which direction the magnetic field is around a current, because of a current that's going through that wire, you put your thumb in the direction of the current and you curl your hand around the wire, and that will tell you the direction that the field is going, because the magnetic field is going to be curving. It's going to be turning around the wire. So that can tell you the direction of current. There are lots of right-hand rules for magnetic fields, and many, many ways you can use them, probably at least a dozen that I use regularly. So you eventually just kind of get used to the fact that if you use your right hand to try to figure something out, you'll eventually figure it out. Otherwise, you're just kind of guessing. But the equation that determines this strength of this field actually comes from some calculus, and they just give it to us here since we don't do the calculus. It's just mu naught times I over 2 pi r. Now, what is mu naught? Mu naught is another constant of the universe called the permeability of free space. Remember, we already dealt with something called the permittivity of free space, which was epsilon naught. This is permeability of free space, mu naught. And mu naught is 4 pi times 10 to the minus 7 Tesla meter per amp. And it is one of the constants of the universe, one of the things that does not change in the universe. There's only a few of them. Mu naught is one, epsilon naught is another, and then there are a few others. But even the speed of light is not actually its own constant of the universe, because speed of light, it turns out, is actually a combination of mu naught and epsilon naught. So it's actually a derived constant of the universe from some laws that we will learn about here soon. So if we want to actually find the current in a long straight wire that is producing a magnetic field twice the strength of the Earth at a distance of 5 centimeters from the wire, we can use this equation to do it. Because the 5 centimeters goes in the R, that's the distance from the wire. The current is the thing we're calculating, and we know that we want something that's twice as much as the Earth's magnetic field. The Earth's field is about 5 times 10 to the minus 5, so we're going to look at something that's about 10 to the 4, 10 to the minus 4 rather. So 1 times 10 to the minus 4, we plug all those numbers in, we get a 25 amp wire, can create a magnetic field 5 centimeters from it, about that far, 2 inches or so. That is twice as strong as Earth's magnetic field. Earth's magnetic field is not that strong in most cases. Okay, so now we're going to get into the laws of electricity and magnetism. And the only reason we've waited this long is because the laws, half of the laws, involve magnetism. The other half involved, the other two laws, there are 4 laws that go together to make Maxwell's equations, which are the laws of electricity and magnetism. 2 of the laws involve electromagnetism, electricity and magnetism combined. The other 2 either just involve electricity or just involve magnetism. So here is the first law, which we call Ampere's law. Ampere's law essentially says, they don't really actually say it anymore, do they? Not really. They should say it somewhere. Anyway, what Ampere's law says is that if you have a current that's moving along and you change that current, you will create a magnetic field. So changing currents or moving currents, either way, and that really just means current in general. Current causes magnetic fields to be formed. And that's all there is to it, really. But the important thing is it doesn't matter if it's the current that is actually changing or if the current is moving. Either way, it works. So either way, if the current changes in some way, or the movement, or if it's just movement of charge, movement of current, it doesn't matter one way or the other. So that's kind of important. And that's the first law that we put into this group of laws. So here is a situation. No, I'm sorry, I lied to you. I told you the wrong law. The one I told you is actually Faraday's law, because they're actually talking about here. Here they're actually saying that it's changing magnetic field creates a current. So we're creating a current, not changing a current. So here is, so Ampere's law is actually the other one. I always mix them up. Ampere's law is if you change the magnetic field near a wire, you will create a current. Now, it sounds very similar to what I just said, but it's actually just the exact opposite. So again, we're running into Newton's third law again, which is opposite equal kind of action-reaction. But in this case, you have a wire that is that you bring to a magnetic field, or you change the magnetic field around or something. You have a wire, you have a magnetic field, you change the magnetic field somehow, and it will create a current in the wire in some way, in the conductor. It doesn't even have to be a wire, it's just a conductor. The interesting thing is that the current that is created is always created in loops, and the current is always created 90 degrees to the change. So in this case, we actually deliberately make a loop of wire to demonstrate how this works. So here's our loop of wire, and then it has no magnetic field through it to start. But if we put a magnetic field through it, if we start one up in there, if we bring a magnetic field close to it, it will create a current in the wire. If you create a current in the wire, it creates a magnetic field. Those two things they seem like the same thing, but they're direct opposites of each other, right? Did I have that right? Did I say it wrong again? I don't know. They never say it in here, so I'm not sure if I told you correct or not. I may have told you right the first time. It doesn't really matter what we call the laws, just so that we know that they exist. But anyway, and they don't actually write it down here either, so it doesn't help. But Ampere's law is one of the laws of this group of equations, one of these group of laws that we're going to put together. And we've got all these equations already, but let's look at one more equation. We've already looked at the equation for the magnetic field at the center of a loop. That's this one here. We've seen it already. If you have a loop of some radius r, you want to calculate the magnetic field in it. It's the current divided by 2 times the radius times this mu naught. And that gives you for one loop. And we had the same thing for more than one loop, because we were talking about torques, and those came from magnetic fields. So if you have more than one loop, you just multiply by n. But the interesting thing is that if you have a whole bunch of loops in these, and they end up making a long loop, a long tube of loops, then you get an interesting thing where the magnetic field inside the solenoid becomes very, very constant. And it can be measured or it can be calculated using this equation, mu naught times the number of loops times I. And that has to be a long tube of loops of wire. And we call it a solenoid. And solenoids are quite useful because of this constant magnetic field that goes down the center of the solenoid. And you can see here down the center of the solenoid, the lines start to get close to parallel. And the longer the solenoid is, the more parallel they become. So you can make a very uniform magnetic field down the center of the solenoid. In this example, they just want us to calculate the field strength inside of a solenoid. They tell us it's 2 meters long and it has 2,000 loops. But little n is actually not just number of loops, it's number of loops per unit length. So we have to take the total number divided by the length to get the number per unit length. Turns out there's 10 per centimeter in this one. And then we multiply all those numbers together. They give us, for this one, the current, the number of loops per unit length, and mu naught, which is the 4 pi times 10 to the minus 7. And we get 2.01 Tesla of magnetic field down the center of this loop. Now, it seems like a huge amount of magnetic field. Well, it was a huge current. 16 amps or 1600 amps is a lot of current, so we would expect a huge field. If you were going to make something like this, a solenoid like this, you have to make it out of copper refrigerator tubing, run the current through the copper refrigerator tubing, and run cold water through the refrigerator tubing as well, so that you don't melt the tubing, because it would get really, really hot. So, we've got some laws that we're putting together here. We're going to talk about forces between conductors, and then we're going to talk about Faraday's law, I assume. Take a look at what we're going to look at here. Faraday's law will be in the next chapter, so we're getting close. Getting close to Faraday's law. So, how do I close this? There we go. So what we've learned so far is that current creates magnetic fields. Those magnetic fields that we create can cause forces to happen, can cause torques to happen. This is all Ampere's law stuff. So now we're going to just look at some different examples of this, different situations with this. Here we have one wire that is creating a magnetic field because we put a current in it, and the magnetic field is going around and around this first wire here. And then there's a second wire over here that also has a current going through it. Now we're not going to think about the magnetic field that the second wire creates. We're just going to think about the force that the first one exerts on the second one. So here's the top view of this. We have the first wire right in the center of this circle, and this circle represents the magnetic field going around this first wire. At the second wire, we have a magnetic field that is pointing up, and we have a current that's coming out of the page. So we put our thumb in the direction of the current, our hand goes up for the right-hand rule, and the force is towards the other wire. Well, if you do the same thing for the other wire and figure out what the force is on the wire on the left, the first wire, you'll find the force also going towards the other wire. So these wires will actually attract each other if the current is going in the same direction. And you can calculate that force using this equation. The force per unit length is going to be mu naught times the first wire current times the second wire's current divided by 2 pi r. So that's the force per unit length between the two wires. Of course, the force on the one wire is going to be equal to the force on the other wire because they have the same current and because they're kind of equal and opposite things going on there in the end. So that's how you measure the force on either of them. It doesn't really matter which one. You have both currents involved, even if the currents are separate because it is an equal and opposite force thing. But it is a force per unit length. This is not a direct force. It's force per unit length. And this is actually how the amp was defined in the end, is using this idea here, and that's one of the reasons they show it. But the other reason that they show it is it's just interesting because what would happen if you switch the directions of the current? These two, when the currents are going the same direction, they attract each other. But when you switch the currents, the right-hand rule is going to change, and the force is going to go outward, and they will repel each other. And again, this becomes an electromagnetic force thing that causes a mechanical force. It causes movement. And again, that can be very useful in the real world, to be able to induce movement from electromagnetic force. Okay, and the last section is about mass spectrometry, which we already talked about, but let's go ahead and talk about it again. Remember that we talked about shooting particles into a magnetic field that have different masses, but the same charge, right, and the same velocity you could consider. So this device over here does a couple of different things. The ion source is essentially like a little oven where you put in whatever you want to study in here, a piece of metal maybe, and it heats it up. And as it heats it up to a certain point, atoms start popping out of the metal, okay? And if it's a metal, let's say it's steel, the atoms that are going to pop out of steel are going to be maybe iron, maybe some nickel, maybe some carbon. Let's say those three things pop out of here. Then you get these atoms that go through these parallel plates and through this device called a velocity selector. It also has a magnetic field in it that is pointing out of the page. But what this does here is that the only atoms that are going to escape from this device are atoms going a specific velocity. If they're going too fast, then they're actually going to hit a wall. And if they're going too slow, they're going to hit another wall. The too fast ones will hit a wall going up. Too slow ones will hit a wall going down. Okay? The ones that are going just the right speed will actually make it right to this little doorway, and they will go into the mass spectrometer. So now every atom that's going into this spectrometer is going the same speed. They're not necessarily the same atoms. They're different masses. Carbon's different than iron, is different than nickel. But they all have the same speed, different masses. But the other thing that this does as they come through here, as they both heat up and come through here, is it selects the charge. So things that are charged too positively are going to get attracted back to up here towards the negative plate and run into this wall up here and miss. things that are charged too negatively are going to run into this one down here. But saying things that have just one positive charge, so they've lost just one electron, are going to go straight through here. That's just how they balance it and make it work. And that's nice, because then you have everything coming out here has a charge of +1, has different masses, and all has the same velocity. Therefore, this equation will work, because everything has the same velocity, everything has the same magnetic field, everything has the same charge. The only thing that affects this is mass. So the radius is directly affected by the mass. If you have a bigger radius, you have a bigger mass. And that's all there is to it. And so they just go out here and they put in their ion source, they put in carbon, or they just calculate the mass of carbon, put mass of carbon in here and calculate the radius, and then they just put a little mark on here that says carbon. This distance is for carbon, this distance over here is for iron, this distance over here is for nickel, this distance over here is for whatever. And then they just put this thing, whatever the thing they're trying to study in there, heat it up, and everything that comes out and hits at the carbon place tells you how much carbon it is. And they make this wall out of phosphor. They put a phosphorus material on here so that it will glow every time a charged particle hits it. And the more charged particles that hit it, the more it will glow. So if it glows a lot in one place, that means you have a lot of that particular material. If it glows less in that place, you have less of that particular material. So it becomes quite a useful little tool. We already talked about cathode ray tubes, magnetic resonance imaging. We used lots, we talked about all that stuff before. So we're going to end this chapter at this point, and I'm going to put the homework, so I'm going to make the homework assignment so that you guys can get started on it if you want, and ask questions of me if you want, before I start my class at 11. So that's all there is for today, and if you want to hang out till the homework is made and done, you're welcome to. If you want to take off, you're welcome to. It's up to you. Have a good day.